This is FRQ assignment number 2, question number 3. A projectile launcher consists of a spring with an attached plate as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any of 3 positions, A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in position C. The sphere is then launched upon release of the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. So, the student plans to test this hypothesis by launching the sphere using the launcher. So we're going to state a basic physics principle or law that you could use in designing this experiment. And I came up with 2. One is conservation of energy, and the other is work kinetic energy theorem. So that's for part A. I'm going to do part A, 1, and 2 together. Part 2 says using a principle or law stated in A part 1, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a high school physics laboratory. So if you said conservation of energy, then the formula you should use, and there's 2 ways you could go about this. If you wanted to launch it horizontally, you could say 1/2 kx squared is equal to 1/2 mv squared and measure the speed of the ball when you launch it using a motion detector. We'll talk about that later. If you wanted to launch it vertically, you could use 1/2 kx squared equals mgh and talk about the maximum height that the sphere attained. So if you said conservation of energy, you could use either of those formulas. You could have also said the work kinetic energy theorem, which sometimes you just think of, right? Work is equal to the change in kinetic energy. So again, the work done by compressing the spring is 1/2 kx squared. And then you could say, well, the initial kinetic energy is 0, and then you could measure the final kinetic energy and then compare those, which is essentially what you're doing here. But just depending on, like, if you said conservation of energy, I would say, well, the initial spring potential energy equals the final kinetic energy. If I said work kinetic energy theorem, I would phrase it like, well, you have to do this much work to compress the spring. That work is converted into the change in kinetic energy of the marble. So either way, you can make that work. 1 point for an equation that's consistent with the principle that you wrote in part 1. 1 point for a valid equation that contains measurable quantities and K. And then 1 point solving for K, which I guess I didn't do. So I did this in my notes. So for this one would be mv squared over x squared. And for this one, it would be K equals 2 mgh over x squared, where x is the amount that it's compressed. So that's part A, 3 points. Now part B is where you design the experiment. So the couple ways that I have described it, if you want to launch the object horizontally, then you're going to use 1/2 kx squared equals 1/2 mv squared. So you're going to measure x with a meter stick or a ruler. You're going to measure the mass using a balance, right? And you're going to measure the velocity. I would just go with a motion detector. Set up a motion detector that's set to capture the speed of the ball right after it's launched. So you'd want to aim it just after that point. So those are things that you could measure. Then if you were going to use 1/2 kx squared equals mgh, well, you'd measure the mass the same way, you'd measure that the same way. You would just use 9.8 or 10 if you wanted to even say that. Now, how are you going to measure the height? So there's a couple ways you could do this. You could, launch it and use, I think I'd use like a camera. I'd set a meter stick along the vertical part there, and then use a camera to watch and see how high it went so that you could pause the camera to measure h. So there's a couple ways you could measure h that would make it work. So for part B, you get 5 points. You get 1 point for listing the relative quantities plus equipment. So you're given a grid here, quantity to be measured, symbol for quantity, and equipment for measurements, 1 point for describing how you would take those measurements, especially the heights there, and when if you're going to measure the speed, you're going to just take a second to explain where you're pointing the motion detector. You get 1 point for a plausible procedure that involves launching from the launcher. They're very specific about that. I don't know what else you would do. I suppose you could take the spring out and hang a mast from it, but they don't want you to do that. They want you to use the launcher. 1 point for launching from at least 2 different positions. Hopefully that's pretty clear. Like when they say you can launch from 3 different positions, you'd never launch from just one. It says launching from at least 2 different positions. Then another point for attempting to reduce uncertainty. So for me, I would say launch from all 3 positions and launch 3 times from all 3 positions. You don't want to say, take 50 different trials because that's unreasonable, but definitely different positions and also multiple trials. So 5 points for part B. Okay, so part C says use the data that you gather to confirm or refute the hypothesis. So you're going to measure what you're going to measure, and you're going to calculate K for all of your different trials. So for part C, you get 1 point for comparing K at all 3 distances. So you want to make sure that you get the same value of K for point A, point B, and point C. Then you get a point for considering uncertainty, right? Numbers aren't going to be exactly the same. So you say something like, those numbers match if the numbers match within experimental uncertainty, or if the numbers are about the same, right? Remember, they don't have to be exactly the same, but say something that lets them know that you're thinking about, they just have to be reasonably close to each other. And that's the 2 points for part C. Finally, for part D, we've somehow found some other marbles that have the same diameter, so they still fit in the launcher, but different masses. So each sphere is launched from the same position, so we're going to consider each sphere's launch speed, which is the speed of the sphere the instant it leaves contact with the plate. So we're going to sketch, right, the graph of launch speed against the sphere mass. So if you did this, 1/2 kx squared equals 1/2 mv squared, then you're kind of set up to do this. Now, here's a really good argument for reading the whole problem, because if you have no idea how you're going to do this experiment, you read on to practice D and you're like, launch speed versus mass, and that gets you here. That was well worth your time, right? So remember, you've seen this more than once. Read the whole problem. I know you're stressed out. I know there's no time to do this, but that could get you started, okay? So now we're going to consider a situation where the mass of this object continues to increase. Well, if the mass is going to increase, what's happening all of this? This is all going to remain constant, right? It's the same spring. It's being pulled back the same distance. So this is constant. So if my mass is going to increase, what's going to happen to the velocity? Well, it's going to decrease, right? But this is not a linear relationship because we have v squared. So your graph is going to look something like this. Okay, now this is something that if you had a couple minutes, you could plug and chug some numbers, but this is our parabolic relationship here. So the rubric goes like this. 1 point if you get a curve where the speed decreases as the mass increases. So you're going to get a point for that, for realizing that as the mass increases, this stays constant and the velocity is going to decrease. So you actually get that point, but you get another point for realizing that the graph is actually concave up, right? And that's the shape here. So that was it for number 3, 12 points for that one. It was actually kind of a short question. So hopefully that made sense.